Hi everyone. Today I'm going to be explaining partial fractions and integrals, chapter 7.4. This concept shows how to integrate any rational function or a ratio of polynomials by expressing it as a sum of simpler fractions, called partial fractions. And then we'll integrate these partial fractions using methods we already know. I'll be demonstrating this concept using the following definite integral bounded by 2 to 4. It is 3x squared plus 1 over x plus 1 times x minus 5 squared. So first we would want to break the denominator into factors if it had not been done already. Here we can see we already have factors. It's as simplified as it can be. So we can move forward. Our next task would be to assess the degree of the denominator versus the degree of the numerator. Here we can see that the degree of our denominator is x cubed, the numerator is x squared. That means the degree of our denominator is in fact greater than or equal to the degree of our numerator. If the numerator degree had been larger, we would need to move forward with long division of the polynomials, but in this case we can move forward, which is very convenient. So next we will be assigning variable letters to our partial fractions since we need to solve for our coefficients. And first we'll start by breaking this apart. So we have a over x plus 1, which is right here, this factor, plus b over x minus 5 plus c over x minus 5 squared. Now the reason why these look different is x plus 1 is a distinct linear factor. This means that it only appears in the denominator once. However, x minus 5 is a repeated linear factor. So based on the exponent here, we will require that many variables. In this case, 2. So we have b and c. And each time the denominator of our partial fractions will go up by one exponent. Okay, so we're going to be addressing the integrand while we solve for our coefficients. It's just simpler that way. So we'll start by multiplying both sides by the denominator of our original function here. And that's going to cancel these two terms out and make our life a lot simpler. We'll also be canceling terms on this side individually. So we'll end up with 3x squared plus 1 equals a times x minus 5 squared plus b times x plus 1 times x minus 5 plus c times x plus 1. Now there are two methods to solving for coefficients. So we're going to choose the easiest one first. The easiest way is to find an x value that we can substitute in that will isolate one of our variables. So there are two that you can probably see right away, and we're going to start with x equals -1. Now if we put that in here, we'll end up with 0b, and we'll also end up with 0c. So when we do that, we end up with 4 on the left equals 36a, so a equals 1/9. And then our second x value that we can sub in is 5, which would get rid of a, and also b. 5 minus 5 is 0. So we end up with 76 on the left. That'll be 5 squared times 3 plus 1 equals 6c. So c equals 38 divided by 3. Now, unfortunately, we still have to solve for b. So we will be addressing the second method of solving for coefficients. So to do that, we're going to expand here, or expand our factors here. And you can see x minus 5 squared becomes x squared minus 10x plus 25. And we also have b times x squared minus 4x minus 5 plus c times x plus 1, which hasn't changed. And we're going to go one step further and factor this all the way out. So we have our individual terms here. Now the next step is to create individual equations based on like terms and solve for the coefficients based on those equations. So you can go about this many different ways, especially because we already have two variables solved. So I'm going to choose our numerical value here just as an example. Here we don't have an x value, it's simply just 1. So on the right side, we will look for coefficients that also do not have an x value. Here we can see there's 25a, negative 5b, and c. So when I do that, I have 1 equals 25a minus 5b plus c. When we sub in the variables that we already know, and we simplify our fractions, we end up with negative 130 over 9 equals negative 5b. So b equals 26 over 9. Now, again, you could go about this multiple ways. You could have chosen your x squared terms and isolated those into their own equation. I've also written 0x here. You don't have to do this, but it can help with visibility to see that you would set up your x terms on the right side equal to 0. So moving forward now, we have the variables we need to create our partial fraction integral. So when we sub those in, we see we now have a definite integral between 2 and 4 of 1/9 over x plus 1 plus 26 over 9 over x minus 5 plus 38 over 3 over x minus 5 squared. So thanks to integral laws, we can focus on each of these individually. So I'm going to start with the first integral, and I am going to solve each definite integral step by step. You could wait till the end to apply the bounds, but I just found it easier to apply the bounds within each integral individually. So our first integral is 1/9 over x plus 1. This is a simple u substitution, so we'll assign u to be x plus 1 and du equals dx. So our integral becomes 1 over 9u, and that integrates to 1/9 times the natural log of the absolute value of u. When we sub u back in, we get 1/9 times the natural log of the absolute value of x plus 1. When we apply our bounds and simplify, we get 1/9 times the natural log of 5 minus 1/9 times the natural log of 3. And we'll be able to simplify that further later when we solve the other integrals. So to keep track, I'm going to place those into our integral equation up here, and now we'll be focusing on the second integral, which is 26 over 9 over x minus 5. U will be x minus 5, and du becomes dx. So we end up with an integral of 26 over 9u, and that integrates to 26 over 9 times the natural log of the absolute value of u. And this is pretty familiar. We sub u back in, 26 over 9 times the natural log of the absolute value of x minus 5, apply our bounds, and simplify. So the natural log of 1 simply becomes 0, and we end up with negative 26 over 9 times the natural log of 3. When that's subbed back in, we can see that these terms here will easily combine. We get 1/9 natural log of 5 minus 27 over 9 natural log of 3 plus our third and final integral, which is 38 over 3 over x minus 5 squared. And this one's a little different, but it's still a basic u substitution. We'll assign u to be x minus 5, du equals dx. So we integrate to 38 over 3 times negative 1 over u. And we sub our u back in, so we get negative 38 over 3 times x minus 5. When we apply our bounds and simplify, we end up with 76 over 9. So when we plug it all in together, we end up with 1/9 natural log of 5 minus 27 over 9 natural log of 3 plus 76 over 9. And it's pretty clear to see this will simplify nicely. Our original integral was a definite integral between 2 and 4. It was 3x squared plus 1 over x plus 1 times x minus 5 squared. And our final answer is natural log of 5 minus 27 natural log of 3 plus 76 over 9. All right, thank you. Have a great day.